Bill Hurd from HACKADAY. Welcome to part 2 of tearing into Delta Sigma analog to digital converters. It's getting harder to say every time. In part 1, I talked about a lot of the theory. I tried to start a fight about quantization error. I haven't yet said quantization. I'm doing good on that one. I talked about oversampling and noise shaping, which are all techniques used in the Delta Sigma converters. Today I'm going to show you the bench. I'm going to show you some stuff I built, the thing I almost built, and we're actually going to throw it on the spectrum analyzer, and we're going to end up with doing a digital filter in FPGA, just as a quick example. So, tearing in a Delta Sigma AD converters part 2. Let's get started. I built a couple different implementations of a Delta Sigma modulator, and let's review before I show you the actual builds on those. Again, here it's comprised of a difference amplifier, an op-amp. It's got an integrator, which is an op-amp with a capacitor. It's got a comparator, which is an op-amp run in open loop gain. And what's missing here is I actually used a clocked comparator where an external clock tells it when to update. So it's a 1-bit flash AD converter. And then a switch that inverts the polarity of the output and feeds it back. I've superimposed the black diagram on our schematic here. Here we see the difference amplifier up in the top corner. Here's our integrator. You see the capacitor there. Here's our comparator. This one is a clocked comparator. This is a clock signal in, and it actually has 2 polarities of output to choose from. And then I'm using a silicon switch to emulate the switch. The first schematic I showed you was called a single order modulator. Here's a dual order modulator, which means we've got 2 things going for us, 2 integrators, we're 2 feedback paths going on, and with the second order it can either do something much better than a first order, or if you screw it up it can do it much worse. I just wanted to show you this because we did build one of these. Unfortunately we didn't have time to really go into it in time for this video. Forgive the weird camera angles here today. We've got a lot going on the bench. Here's our first order modulator that I built. Pretty straightforward. SMA connectors for to get the signal on and off. I performed okay. Had a little bit of problem with saturation in one direction, but it's alright. One of the ways I looked at building one was also using a PSOC5. You can actually push the components around in the GUI for that, and there's even a digital filter in there. It turned out to be the wrong kind, but we may talk about this with digital filters. But it's pretty cool what you can do for $10. Here's a module that is, it's a dedicated Delta Sigma modulator, and this one's actually isolated, and I'll show you what that means. But this one was a fixed clock frequency, and I ended up using a multiple clock frequency ones to show you some of what we want to do here today. And then this just arrived. This is the circuit board for the dual pole home-built Delta Sigma modulator, but it's too late. I need to get this video done or I'm going to get fired. Here's the data sheet for the Analog Devices 7403 Sigma Delta modulator that I ended up using. It's a self-contained modulator. In this case, by being isolated, what we mean is there's separate power supplies for the input circuit and the output circuit, and there's electromagnetic coupling in the middle. Well, this is useful in instrumentation, and we actually asked this in the comment section of the last analog to digital post I did. How do you create this isolation? In some cases you do it on the output. This one's done closer to the input. Say 1,000 volts got shorted to your analog and you don't want it to get into the computer measuring it. This is the typical of isolation. This is a good place to do isolation because there's only 2 bits we have to isolate. There's the clock, and there's versions of this where the clock is an output instead of an input. Same thing though, we just isolate 1 bit for the clock and 1 bit for the data. We don't have to do 16 or 24 bits for the data. So this is the guy on the bench, and let me show you some of the scope on this guy, show you how he's working. Here's the output of the modulator as seen with the sine wave, and you can see the variations at the highs and the lows. Here with the square wave I did this just to kind of show you the contrast between the 2 highs and low signals. Still looks like gobbledygook. And then a triangle wave. So believe it or not, there's stuff encoded in here, and we're going to look at that closer. But there really is. Here's nothing, so you would expect random stuff to look random. And then back to a sine wave. Here's a live output of the Delta Sigma modulator, and I'm going to freeze it, and we can see a single snapshot of the interpretation of a sine wave. So back to run, hides my sine wave a little bit. But is there really a sine wave in there? Well, I'm going to use a function on the scope called average, and you can see it build it down. There's noise, of course, and I can change the size of the average. So there's 32. I'm actually surprised it works this good with an average of 16 samples, but then all the way up to 512. And lo and behold, there's really a signal modulated just in that digital output like that. All right, back in the frequency domain. Remember, to the left is a low frequency, to the right is a high frequency. And this is a spectrum analyzer that shows us this. This running a FFT, a fast Fourier transform, to display this. And then I've got a signal generator hooked up. And remember what we said, that oversampling by 4 gets us another effective bit of resolution. In other words, approximately 6 dB. So let's go ahead and change our sample frequency, which is currently 5 megahertz, as you can see here. If we change it to 20 megahertz, now watch the screen, watch the noise baseline. Boom, down it goes. Matter of fact, it uncovered some noise. Good for us. But right there it is. It actually works. We did it by a factor of 4 and dropped our noise. We'll take it back to 5 megahertz. And the noise floor will come up on us. You'll see we have a lot less room between the top and our noise now. So oversampling works. This is cool. If you remember this drawing where we showed noise shaping, where we tried to push the noise into a curve shooting off to the right, the higher frequencies, remember later we want to digitally pass this so that only this part gets through. But remember this, where we did this. Let's see if this is also taking effect now. All right, I've expanded the span on the spectrum analyzer here, so it's 2 megahertz from side to side. It was a lot smaller earlier. And sure enough, here is our hump from our digital noise shaping over here on the left. Now let's watch what happens when I once again re-increase the sample frequency by a factor of 4 up to 20 megahertz. Boom, and down it goes. Again, we've uncovered our noise. And now the hump is shoved even further off to the right. And so our techniques have really bought us some signal to noise ratio here in a positive way. Back to our block diagram of the sigma delta analog to digital converter, the whole thing. We've just gone over the modulator in detail here, creating this type waveform. So now we have 2 more pieces remaining. We have the integrator, the digital filter that combines and averages these pulses and turns in the single bit pulse and turns it into a multi-bit pulse or / number that we can use internally. And then the decimator, which then takes this overabundance information. You saw it on the spectrum analyzer, all that information, but all the stuff we were interested in was way off to the left. So we want to decimate ourselves, which means to remove the unwanted stuff, and you can look up what it means. It's an interesting story. But we remove it down to just the amount of sampling we need to get the job done. I'm showing the logic behind both sets of digital filters simultaneously here. And so one way to realize what we're doing is there's 2 clocks. There's 2 clock domains. There's a clock on the input and a clock on the output, because they're 2 different frequencies. One's the high frequency of all those bits streaming in. The other is the lower frequency of the final decimated value at the sample frequency that we want to end up with. So, and here's how we read this, is the input signal goes through a summation and a time delay. Z is a time delay of, whatever amount, in this case 1 clock, and it feeds back some of that and gets summed in again, but also goes on to the next stage, which does the same thing, a delay in the next stage. So this is an averaging filter, a moving averaging filter, where the output coming out of here is the average of going through all these steps of summing with itself and ending up with a number that has noise filtered out of it also, because of the way summing works and integrating. Coming out of our integrating accumulation process, now we go to the decimator. So this drops down to here, and now we see in the summation that it's starting to subtract it out. And again, the same thing. These are Z as a time delay, and we are taking the results, removing information from it at a different rate, and finally we get our output. The combination of these two is sometimes called a CIC filter, cascade integrating comb filter. I'll show that a little bit more. It's also, it's called a sync filter, S-I-N-C, which refers to the sign and nature of it and where it's centered and stuff. Here in the data sheet for the AD7403, it's such a good data sheet that they go ahead and show us the characteristics needed for the digital filter. They show us the curves and the decimation rate and everything. And then they actually give us an example in Verilog of a digital filter. And if we look here, here's our accumulator function that I showed. Here's our decimation function that I showed. And then they show the different rates to program it for the different responses to get you going. So what I'm going to do is I'm going to just snag this bit of code. In reality, I had to do some typo fixing. But we're going to snag this bit of code and we're going to drop it into the FPGA. All right, I'm going to run you through the process real fast, way too fast, for creating a digital filter based on having a piece of Verilog as your filter. And I'm going to do this in Quartus. I'm actually using Quartus 15, which is fairly modern. I use a lot of the old Quartuses sometimes, depending on what I'm doing. But let's get started. So the first thing I'm going to do is I'm going to import my assignments for the PC board I'm using. I've already worked with it before. I've got a little assignment thing. Boom. Don't need to make a backup. Boom. And there's all my pins and everything that I'll need and the pin numbers. So this matches to my board. So go back to Project Navigator, do Files, add remove files from project. And here is our decimator as our digital filter as a Verilog file. I like to start with a top schematic file. It's just habit of mine, so we're going to do that. I'm going to switch. So here it is. This is typed in. This is the what you saw in the data sheet. So we are now going to create a symbol for this, which will actually compile it. All right, it says it created the symbol successfully. I'm going to go back to my top sheet. I'm going to insert a symbol. There's the symbol for the Verilog that we did. And I can now do generate pins for symbols. And I would go in and number these if they weren't already assigned. Now, the reason why I use the top sheet, a lot of times I add test points and all kinds of other things. So let's go ahead and compile this again. Okay, full compilation was successful. Normally I would go into my model sim and create simulation, all that good stuff. But that's what I've been doing the last week. So I'm going to go ahead and program it. Output files and start. Okay. It's now running on the bench doing that piece of Verilog code that we looked at. This code right here. And that's one way to get your digital filter. And again, we talked about what are FPGAs good for? Well, this is one of the things. You could have whole bunches of these running in parallel, all kinds of things. Remember, code that can't work in parallel typically. Code works a single instruction at a time. By code, I mean in a microprocessor. Now, let me show you another way to do a filter in Altera. I'm sure that Xilinx can do this as well. They all have what they call their VIP suites or their high-end suites of tools. In this case, we're going to go into a thing called QSys, which is a system builder. All right. And I've been in here already playing around with a little bit, but if we go to the filter specification, turns out I can choose different kinds of filters that are pre-built. There is a finite infinite response. Finite impulse response type filter, which has the coefficients and stuff we're all used to, and that's for a different video. Then we have the CIC, the Cascade Integrator Comb Filter that we're working on, so I've selected that. And in here, we decide what kind of stage. We've already said it's a decimator. We set the number of stages, the differential delay, different factors in it. And at the end of the day, these combine to make our output data width. And so built in right to Altera's toolset is a CIC filter. So here's another way to do it. We generate our HDL. We even tell it we want it to, well, that's the simulation model, but we said, do you want to generate this code as Verilog or VHDL? I tend to do Verilog. And boom, now we're making a filter programmed from a wizard. And there's advantages and disadvantages, but I wanted to show this to you. Again, if you were doing an FIR filter, you can do this and still go outside and build your coefficients in MacLeod, or I found an Excel spreadsheet online, and I found a guy that's got a filter builder online where you can copy the coefficients from and bring them into Verilog, or I'm sorry, into Quartus. Okay, it tells me it's finished compiling. It closed. We can actually get out of. We'll just minimize it. And now when we go to insert a symbol, there's a symbol for the device we just built, and it's got a lot more things. You can go in and manage the different control signals. It uses something. It uses a custom bus that's got called the Avalon bus. So it's got like ready and wait and signals like that. But again, if you want to shortcut it, we just generate pins for all these, run them together, and now we've got a filter built with a wizard inside of Quartus. Alright, we're on the home stretch here. I wanted to show, I've been playing like for a while here, getting ready for this video with different things. I have an analog evaluation board here, ADC evaluation. And remember, I'm always doing little R2R DACs. Well, now I've got my own a DAC chip that happened to be parallel. This was a parallel card, and I was streaming information from ADC back to DAC and doing different things. But at the end of the day, didn't do much for us. But I'm going to show you this. This is an evaluation board that cost me too much money. Don't tell my wife. For Delta Sigma, Sigma Delta type ADC converters, but allows us to interactively change the decimation rate, things like that. So let's play with this here right in the end. All right, here's a board. I honestly thought it'd be more useful for showing you the actual manipulation of the digital data, but I was wrong. But let me show it to you what it is useful for. So it does have the FPGA stuff I was doing with the RAM, and this has an interactive control of a device similar to the one we used. This is a full system called the AD7760. Of course, it needed SMB connectors and XLR, so I had to get all that working. And at the end of the day, what we got was this interface right here. And at first glance, well, it is kind of cool. I've got it frozen right now. Let's put it, we can see the waveform. We can see the frequency domain. So time domain here, frequency domain here. Let's put it in a continuous operation. This goes useless. But here is our FFT that we're used to in the frequency domain. And what was interesting is I could go in here and I could actually change the filter. There's filter default coefficient depth, basically, I can set. You can import file folders or files of filter coefficients. We can manipulate things like the overrange and that kind of stuff. We can take a look at the modulator output. Oh, what's this? Is that noise shaping going on? Yes, it is. And then we've got things like the number of samples we use on the input. And watch, I just set it to a high number, and it's going to slow down but go down. All right, so we're integrating in our CRC filter at the front part of it. We're integrating a whole bunch of samples, 524,000 in this case. Let's go back to something useful. And then our decimation rate. Remember the part we end up dividing it down for. Now, if you do it without really taking care of your data, you end up changing the frequency you think you're spotting if you decimate at an improper rate. And so that's one thing cool about this. So I know the frequency I'm putting into it, so I set it back, and there's my correct value. So kind of interesting display. If you were researching or using this part, it's very interesting because it gives you the actual total harmonic distortion, the signal to noise ratio, everything is spelled, spurious frequency, everything is spelled out for you as measured. So it actually is very good if you're doing this for real and not 2 minutes in a video. All right, in the words of Chevy Chase, Spock, frankly, Captain, I'm exhausted. We covered a lot of ground. Hopefully this gives you a better understanding than I left last time, frankly, about AD converters and noise and the artifacts of resolution, that kind of thing. Who knows, maybe someday I'll have need to stuff my little Sigma Delta modulator. It's a 2-pole, by the way. So with that said, Bill Hurd from HACKADAY. Hope to catch you on the next one. Maybe we'll tackle something not quite so long and complicated. Maybe I'll mega squirt my car. Bill Hurd from HACKADAY. Have a good one.